252 million years ago, the Earth almost died. The fossil record, usually a steady ledger of biological evolution, abruptly plunges into a chilling void. Paleontologists call it the Permian-Triassic Extinction, but its sheer scale has earned it a much darker moniker, the Great Dying. Up to 90% of all marine species and 70% of terrestrial vertebrate species were erased from existence in what appears to be a geological blink of an eye. Forests vanished, coral reefs dissolved, and the oceans became stagnant graveyards. What cosmic or planetary force could orchestrate an apocalypse so absolute that it nearly sterilized our world? For decades, researchers scoured the globe for an impact crater, anticipating a celestial assassin similar to the asteroid that would later doom the dinosaurs. Yet the scarred rock layers of the late Permian period yielded no extraterrestrial iridium anomalies, no shattered quartz indicating a sudden violent strike from above. The culprit was not an invader from the outer solar system, but a monster awakening deep within the Earth itself. Our investigation turns to a vast, desolate expanse in modern-day Russia, a region known as the Siberian Traps. Today, it is a staggering landscape of stepped hills and rugged terrain, but its serene appearance masks a violent past. Geologists have identified this area as the site of the most colossal volcanic eruption in our planet's history. This was not a single conical mountain blowing its top, but a continent-shattering network of fissures that tore open the crust, bleeding molten rock for hundreds of thousands of years. The volume of magma expelled during this event defies human comprehension. Scientists estimate that over 3 million cubic kilometers of flood basalts poured across the ancient supercontinent of Pangaea. If spread evenly, this ocean of lava could bury the entire contiguous United States beneath a layer of rock nearly a kilometer deep. The sheer mechanical devastation of the lava flows was localized, destroying regional ecosystems, but the true lethality of the Siberian Traps lay not in the magma itself, but in the invisible gases it released. To understand how a regional eruption triggered a global biological collapse, we must look at the atmospheric chemistry locked within ancient sedimentary rocks. As the massive magma plumes rose from the Earth's mantle, they did not just breach the surface. They intruded into massive underground basins filled with thick deposits of coal, oil, and carbonate rocks. This subterranean inferno acted as a planetary-scale incinerator. Geological records indicate that this interaction released unfathomable quantities of carbon dioxide and methane directly into the late Permian atmosphere. The sudden injection of these greenhouse gases initiated a catastrophic climate cascade. Isotopic analysis of fossilized tooth enamel and ancient soil carbonates reveals that global temperatures skyrocketed by roughly 10 degrees Celsius. This hyperthermal event transformed lush, temperate zones into scorching deserts and pushed tropical regions past the thermal limits of complex life. The heat alone was devastating, but the atmospheric carbon was only the first domino to fall in a complex chain reaction of environmental degradation. The oceans absorbed the brunt of this atmospheric poisoning. When immense volumes of carbon dioxide dissolve into seawater, they form carbonic acid, fundamentally altering the ocean's chemical balance. The Permian-Triassic boundary marks a period of severe global ocean acidification. Paleontological evidence shows a sudden, massive die-off of marine organisms that relied on calcium carbonate to build their shells and skeletons. Corals, brachiopods, and countless microscopic plankton literally dissolved in the corrosive waters, collapsing the foundation of the marine food web. As the oceans warmed and acidified, they also lost their ability to hold dissolved oxygen. This condition, known as severe anoxia, spread from the deep abyssal plains to the shallow continental shelves. Chemical markers in sedimentary rocks from this era point to seas dominated by anaerobic bacteria, which are microbes that thrive in oxygen-starved environments. These bacteria produced hydrogen sulfide gas as a metabolic byproduct, turning the coastal waters toxic and potentially releasing a lethal, rotten egg-scented miasma into the atmosphere. Piecing together this complex timeline of devastation requires immense precision. How do scientists confidently link the timing of the Siberian Traps to the mass extinction event? The answer lies in microscopic time capsules called zircon crystals. These incredibly durable minerals form within cooling magma and trap trace amounts of radioactive uranium. By measuring the slow, steady decay of this uranium into lead, researchers can pinpoint the exact age of the volcanic rock with astonishing accuracy. High-precision radiometric dating has aligned the peak eruptions of the Siberian Traps directly with the sudden disappearance of species in the fossil record. The data confirms that the biological collapse did not happen over millions of years of gradual decline, but was compressed into a terrifyingly brief geological window, perhaps lasting less than 60,000 years. This temporal alignment transformed the volcanic theory from a plausible hypothesis into the prevailing explanation for the Great Dying. Yet anomalies within the data continued to puzzle the scientific community. If volcanic outgassing alone was responsible, the math did not perfectly align. The volume of carbon dioxide released purely from the mantle magma seemed insufficient to cause such extreme global warming. This discrepancy forced geologists to look deeper into the specific geography of the Siberian basin. The critical factor was what the magma was burning as it forced its way upward through the Earth's crust. The Siberian lithosphere was uniquely primed for disaster. It contained extensive evaporite deposits, which are thick layers of ancient salt left behind by dried-up seas. When the intrusive magma superheated these salt layers, it triggered massive chemical reactions, releasing vast plumes of toxic halocarbons, including methyl chloride and methyl bromide. These ozone-destroying chemicals rocketed into the stratosphere, stripping away the planet's protective shield against ultraviolet radiation. The evidence for this ozone collapse is profoundly unsettling. Paleobotanists examining fossilized pollen and spores from the end of the Permian period discovered a staggering increase in malformed and mutated plant cells. These microscopic deformities are consistent with severe ultraviolet radiation damage. Without the ozone layer, the sun itself became a lethal force, sterilizing the land and destroying the reproductive capabilities of the planet's surviving flora. The forests simply stopped regenerating. The compounding horrors of the Permian-Triassic extinction reveal a terrifying truth about planetary ecosystems. They are vulnerable to synergistic collapse. No single factor, whether the heat, the acid, or the radiation, acted alone. Instead, the volcanic activity of the Siberian Traps initiated a feedback loop where each environmental stressor amplified the others. As forests died, their roots no longer held the soil, leading to massive erosion that choked the already suffocating oceans with toxic sediment. The shadow of this devastation stretched across the entire supercontinent. The terrestrial landscape was reduced to a fungal-dominated wasteland, as decomposers feasted on the decaying remains of forests and fauna. This fungal spike, a brief but massive surge in fungal spores found in the fossil record right at the extinction boundary, serves as a grim testament to the sheer volume of dead organic matter blanketing the Earth. It was a world inherited by scavengers and microbes. Researchers studying this ancient apocalypse often draw unsettling parallels to the mechanics of modern atmospheric chemistry. The rapid injection of carbon isotopes into the Permian atmosphere mirrors shifts in global carbon cycles observed in other geological eras. While the scale of the Siberian Traps is entirely unmatched in human history, the physical mechanisms of greenhouse warming, ocean acidification, and anoxia remain fundamental constants of Earth's climate system. The Great Dying serves as a supreme cautionary tale of tipping points. To truly grasp the magnitude of the event, we must consider what was lost. The Permian period was a vibrant era, characterized by complex ecosystems that looked vastly different from our own. The land was ruled by synapsids, a diverse group of proto-mammals that included the sail-backed Dimetrodon and massive armored herbivores. These bizarre and majestic creatures, representing millions of years of evolutionary triumph, were almost entirely wiped out, their lineages abruptly severed by the atmospheric poison. The oceans were equally alien and diverse, teeming with trilobites, sea scorpions, and dense forests of crinoids, or sea lilies. The trilobites, one of the most successful classes of marine animals that had survived for hundreds of millions of years through previous extinction events, finally met their end in the acidic, oxygen-starved waters of the late Permian. Their disappearance marks a profound severing of a biological thread that had woven through the ocean since the Cambrian explosion. A lingering question haunts the geological community. What triggered the Siberian Traps in the first place? The sheer volume of magma suggests a mantle plume, which is a colossal upwelling of abnormally hot rock from deep within the Earth near the core mantle boundary. Yet the exact mechanics of why these plumes form and why this specific plume was so exceptionally massive and long-lasting remain heavily debated. It represents a fundamental gap in our understanding of the deep geological forces that shape our world. Some geophysicists hypothesize that the assembly of the supercontinent Pangaea itself played a role. The massive landmass may have acted as a thermal blanket, trapping heat in the mantle below until it catastrophically breached the crust. Others suggest that deep Earth dynamics, perhaps related to the sinking of ancient tectonic plates into the lower mantle, triggered a massive displacement of heat. The true origin of the magma remains buried thousands of kilometers beneath our feet. The aftermath of the eruption was a period of prolonged planetary trauma. The recovery of life did not begin immediately after the lava stopped flowing. In fact, the early Triassic period, immediately following the extinction, is characterized by a coal gap, a period of several million years where no coal was formed worldwide. This indicates that peat-forming plants and complex forest ecosystems were entirely absent from the Earth. The terrestrial biosphere was fundamentally broken. During this bleak recovery phase, the world was populated by disaster taxa, which are hardy, unspecialized species that could survive in the harsh, unpredictable environments left behind. Lystrosaurus, a pig-sized burrowing herbivore, became remarkably dominant, at one point making up the vast majority of all terrestrial vertebrates. Their survival, while a testament to biological resilience, highlights the extreme impoverishment of the global ecosystem. Life was holding on by the narrowest of margins. Yet the slate had been violently wiped clean, creating an evolutionary vacuum. As the Earth's system slowly stabilized over millions of years, the survivors began to radiate into the empty ecological niches. The destruction of the dominant Permian fauna paved the way for the rise of entirely new lineages. Among these opportunistic survivors were the archosaurs, the ancestors of crocodiles, pterosaurs, and eventually, the dinosaurs. The modern biological world was born from the ashes of the Siberian Traps. We are left to ponder the fragile nature of planetary habitability. The Earth is a dynamic living system, capable of nurturing incredible diversity, but also capable of unleashing catastrophic resets. The ancient rock layers of Siberia stand as a silent monument to the power of the deep Earth to rewrite the destiny of the surface. It challenges our perception of stability, reminding us that the ground beneath us is part of an active, evolving machine. The Permian-Triassic extinction remains the ultimate cold case of paleontology and geology. By exploring the scars left by the Siberian Traps, we uncover the intricate, terrifying connections between the Earth's interior, its atmosphere, and the delicate web of life. The Great Dying was not just an end, but a brutal crucible that forged the ancestors of the world we know today. It is a stark, awe-inspiring testament to the resilience of life in the face of absolute planetary-scale devastation.